Suppose you're walking around and you come upon a well, and as one does, you hold a rock out and you drop it down the well. Let's say you hold the rock out at arm's length, which is about 1 meter above the ground, and let's say that the rock falls for 3 seconds. The question is, how deep is the well? Now on Earth, gravity has a force of acceleration of 9.8 meters per second. That means no matter how fast something is falling, it's going to fall faster and faster, and in particular, it's going to accelerate at 9.8 meters per second every second. So its speed increases by 9.8 meters per second each second. What we want to do is get some equations going. Eventually what I want is an equation for the position of the ball, but that's not really what I have right now. What I have is its acceleration. I know its acceleration is 9.8 meters per second, and I also know that acceleration is the derivative of velocity, and the velocity is the derivative of position, so velocity will give me position eventually. So let's say that I want some function v of t. Well, let's say t is measured in seconds because it fell for 3 seconds, and let's say that velocity is measured in meters per second, which again is going to make sense since it's accelerating at 9.8 meters per second. Well, what I know about velocity is I know that its derivative is this constant acceleration, 9.8 meters per second. Now, if something has a constant derivative, that means that something is a line, right? The only kind of curve that has a constant rate of change is a line. So that means my velocity is a line with slope 9.8. So it's going to be 9.8 t plus some constant, we'll call c. Let's figure out that constant real fast. Well, if I'm at 0 seconds, that's right when I release the ball, then my velocity is going to be 9.8 times 0 plus c, which is just going to be c. But when I just release the ball, if I don't toss it down, if I just drop it, my velocity is going to be 0. So actually in this case, c is equal to 0. So let's say that the equation of our velocity is 9.8 times t. Now that we have velocity, the thing we want is the position function. Let's call the position function s of t. And do recall that s prime of t is going to be my velocity, which is 9.8 times t. When I take the derivative of a polynomial, if my variable is raised to a power, the power is going to drop by 1. So if my derivative is t to the first, my actual function probably has a t to the second, because when I differentiate it, the power is going to drop by 1. Now what else is going to happen when I differentiate this? When I differentiate it, I'm going to multiply that 2 out. Now what I want to have is 9.8 times t, but since I'm going to multiply by 2 when I differentiate, I should divide by 2 to figure out my position function. Now, when I differentiate this, I'm going to bring down the 2 and it's going to cancel, and I'm going to get 9.8 t just like I like. But something to remember is that I could have, again, had a little constant out here, because when I differentiate a constant, it just goes away. Now again, let's figure out what that constant is equal to. S of 0 is going to be 9.8 over 2 times 0 squared plus c, which is just c. But where does the ball start? Now I'm going to make a choice that the ball starts at position -1, and here's why. If I impose an axis here, I want the ground to be 0, and I want the bottom of my well, wherever it is, to be, s of t, which is going to be a positive number. So that means that where the ball started was actually -1. So that gives us a position function of 9.8 over 2t squared minus 1. Now that I know my position function, and I know when the rock hit the ground, I can figure out what position it was at when it hit the ground. It hit the ground at 3 seconds. So this is 9.8 divided by 2 times 3 squared minus 1. That's going to give me s of t at time 3, which is the position of my rock when it hit the ground. And if we figure this out, 9.8 times 9 divided by 2 is 44.1. So the depth of my well is 43.1 meters.